Okay, so this is for the practice question on Capital 21. So we'll start on the first question. Uh, so the first question is want you to write or find out the product forms when uranium-238 undergo alpha emission. So from the given questions, and we know we will have the starting nucleus. The starting nucleus is uranium-238. And you go to the periodic table, you find out atomic number for uranium is 92. Okay, so we'll take this nucleus as one reactant, as only one reactant, and by the question, it undergoes alpha emission, which means it will emit alpha particle. Alpha particle is a helium nucleus. So therefore, we have our first product. And then we want to find out what will be our second product. So second product is unknown. We will give that chemical symbol called X. And then we will call that atomic number for X is Z, mass number is A. So we will give this X is the chemical symbol for the unknown element or the second product, and Z is the atomic number of the unknown element, and A is the mass number of the unknown element. So A mass number is in one nucleus. So next, because we need to balance atomic number, so the starting atomic number is 92, and we have one product has atomic number 2, the other one is Z, so therefore we have this 92 equals 2 plus Z. And we solve this equation for Z, we get Z equals 92 minus 2 equals 90. Okay, so once we find out this Z atomic number is 90, so therefore we can so this equals 90, and then we can use the periodic table to find out the identity of 90. So the identity of 90 is thorium. So therefore, we find out the unknown element is thorium, and so therefore we can rewrite thorium in the TH here, and 90 the atomic number, and we still have our first product, helium or alpha particle, which is atomic number 2, mass number 4. We still have our reactant, uranium-238, and 92 is the atomic number. So next, we want to find out what is the mass number here for this thorium. So you need to use the idea of balance the mass number and balance atomic number. So now we want to balance the mass number. So the starting nucleus mass number 238, so therefore 238 equals the mass number of all those products. So we have 4 for the helium nucleus or the alpha particles, and A for the unknown element. So therefore we have 238 equals 4 plus A. Solving this equation, we get solving this equation for A, we get A equal to 238 minus 4, so equal to 234. So therefore, we find out our other product is thorium-234. So therefore, the answer is D, thorium-234, or thorium-234. So next question, question number 2, is the radioactive decay of uranium-238 occurs in multiple steps called radioactive decay chain. The second product produced in this chain is the protactinium-234 or Pa-234. We saw the following process could lead to this product starting with uranium-238. So we have a few choices, and most of them has a combination, one step, or first step, second step. So we compare the starting nucleus, uranium-238, with the ending nucleus, Pa-234, we see that the mass number decreased by 4. The common nuclear decays are we studied in this course in alpha emission, beta emission, gamma emission, positron emission, and electron capture. So among those common nuclear decay, only alpha decay can change the mass number. One alpha decay will decrease the mass number by 4. So therefore, for the given problem, if the mass number decreases by 4 in 2 steps, and there must be one and only one alpha decay. Okay, so now let's assuming if the alpha decay is in the first step, then we have the following equation. So we start with our uranium, which we know the atomic number is 292, then the mass number 238. So let's assuming our first step has alpha decay. So therefore, the first step will produce the alpha particle, which is the helium-24. And then we need to find out what will be the second product. The second product we can find out similarly as in question 1. So we have to first find out what is this Z number here, atomic number. So by balance atomic number, we start with 92. So therefore, we will say 92 equals 2 plus Z. And solving this equation, we find out Z equals 90. So therefore, we see 90, you go to the periodic table, is solvent, TH. So therefore, we find out our identity of our second product, which is the solvent. Right. So now we will identify our second product as thorium 90. So similarly, we want to find out what is the mass number by balance the mass number. So we start with 238. Mass number should be balanced. So here we want to balance the mass number. 238 equals 4 plus, we call that A. So A here. And then you solve this for A, so A equals 234. Now we find out both products in the first step. So therefore, we can go on with the possibility for the second step. So this is 234, thorium 234. Okay, so now the second step must start with the product of the first step. We're not going to start with alpha particle. So we'll start with this thorium 234. And then we identify what will be the decay mode for the second step. But that depends on the information of the problem. So the question tells us the product after the 2-step is protactinium 234. Therefore, we know for sure one product will be Pa and 234. So then you go to the periodic table, you see what is the atomic number of protactinium. It turned out 91. So now we'll see what will be our other product. So it's the same idea. We call that X. Then we want to balance the atomic number. So therefore, we have 90 equals 91 plus Z. And solving this equation, we get Z equals -1. So -1, that means it is an electron or the beta particle. Therefore, we pretty much find out the identity of the decay mode of the second step. So finish this problem, I'll make sure it's right. We check the mass numbers. We have 234 equals 234 plus A. So that means A equals 0. So that's exactly the identity of alpha particle. Because alpha particle, it has mass but don't have mass number. So therefore it's 0. Right. So therefore, if we start with alpha decay in the first step, the second step must be beta emission. So therefore, we have this combination of two steps. One possibility of this two-step combination is alpha followed by the beta. Okay, so what about if the alpha particle alpha decay in the second step? Then we will have this equation for the second step. So we know the second step, we must produce the alpha node. So we're assuming the second step is alpha decay. Then from the question, we know we also must produce that Pa234. So if we know the two products, we can identify what is the starting nucleus. So we call that X, and then Z, then A, and then we can say using the balance atomic number, so Z will equals 2 plus 91. So that equals 93. And 93, so 93, that is, you go to the periodic table, that is Newtonian. So we know our identity of the starting nucleus in the second step, which is 93, which is Newtonian. So let's write 93 here. And then we'll erase this X because we already find out the identity of our starting nucleus in the second step, which is Newtonian. So that has a kind of a simple NP. So similarly, we want to balance atomic number, mass number. So therefore, A equals 4 plus 234 equals 238. And now we can replace the A by 238. Okay, so now if we know we have this starting nucleus in the second step, so the second step starting nucleus must be produced from the first step. So therefore, we will know the product or one of the product in the first step will be NP 93 to 38. And then we know from the given problem, the starting nucleus in the first step must start with uranium 238. So uranium 92 and then 238. All right, so from this, we can find out what will be the identity for the other particle in the first step, because if we call that X again, then atomic number Z, then number A here, and then we can say 92 equals 93 plus Z, and then solving this equation for Z, so Z equals 91. And similarly, if we solving the equation for the mass number, so 238 equals 238 plus A, then we find out A equals 0. Okay, so now we find out our atomic number for the unknown particle is 91. 91 will be the beta particles or the electrons. So therefore, we know everything here for this second product of the first step. So we know that will be the electron 91 atomic number and 0. So therefore, this first step decay mode is beta emission. So therefore, in summary, for our second assumption, if we have the alpha decay in the second step, then the first step must be the beta decay. So therefore, we have the second possibility is alpha decay followed by the beta decay followed by the alpha decay in this assumption. So therefore, in summary, we can either have the alpha beta or beta alpha. So therefore, you check all those given answers, so there's only one of these two possible combination, alpha beta or beta alpha. So therefore, the answer is A. Okay, so question number 3 is predict the mode of decay of cobalt 60. So for those type of problem, you pretty much just say the ratio of the neutron to the proton. So if I give you a notation like that, so then you know this 60 is the mass number. And then you know mass number equals number of proton plus number of neutron. So therefore, number of neutron will equals mass number minus atomic number. Atomic number equals number of proton. So those are just some name. Atomic number equals number of proton. So you can write 1 and 1 for proton. So therefore, take the 60, which is the mass number, minus atomic number. You have to use a periodic table to find out atomic number for cobalt is 27. Therefore, you find out for this given nucleus of cobalt 60, the number of neutrons is 33. So then you want to take the neutron to proton ratio. You just take the neutron number, which is 33, divided by the proton number 27, equals 1.22. And then we use this the belt of stability, and we can see near atomic number 27, the ideal ratio is 1.15. Okay, so you can see here, there's one example for this Fe26. The ratio between neutron and proton is 1.15. And what we have for cobalt 60, the neutron to proton ratio is 1.22. So that means this cobalt 60 is somewhere here above this stability belt. So therefore, you want to reduce, we need to reduce this 1.22 to somewhere about 1.15. How can we do that? A ratio is a fraction, so you have to think about to reduce the numerator or increase the denominator. So then in the beta, so-called beta emission, so you think about how we produce a beta particle with a high speed electron, so like that. And you think about in the nucleus, what we have is neutron and proton. So the best choice is starting with a neutron and then produce a beta particle, a high speed electron, then produce the proton. So you can see the equation, the balance, 0 equals -1 plus 1, 1 equals 0 plus 1. So therefore, we can think about when the beta emission happens, actually for every beta emission, you will decrease the number of neutrons by 1 and increase number of protons by 1. So therefore, if this neutron number decreases and the proton number increases, if I draw the arrows, so this goes down, that goes up, and then you can just think about this can goes down. So therefore, that can getting closer to 1.15 and become stable. So therefore, we predict for this given nucleus, so it will decay with the beta emission, and therefore the answer is B. Question number 4 is about write those condensed version of nuclear reaction equations. So some of those nuclear transmutant, and we can bombard some of those target nucleus by some of those small particles like proton, neutron. and to produce the product nucleus. So this is the usual way to write equations, whether it's a chemical equation or nuclear chemical equations, to have a rectangle product. So then those scientists devised an easy way to write those equations, and this is kind of the template for the condensed notation. And you can see in the template, you will see this. So one atomic iso2 simple is a so-called target nucleus. So you write atomic number, mass number, then chemical symbols. Then inside the parentheses, you have those so-called bombarding particles. So this actually will be our reactant particles. And this also reactant. So these two are reactant. And then you have this so-called ejectate. So that word makes sense. Ejectate. So that's ejectate particle, which is one of those products. And then obviously this is also product. So therefore, pretty much in the condensed notation template, you can think about this line here. So before this comma, those are the reactant. After the comma are the product. So sometimes you can see there's a little like swapping the position. So you might write the product nucleus first in the equation and those small particles after. But in the condensed notation, you always write the small particle in the parentheses, which means before the other product nucleus. Okay, so therefore we start with the two reactants. So we'll use the parentheses, and then the particle for the inside. So this H11, which means proton, and then we write the other reactant. The other reactant will be the oxygen 18, and you want to write the atomic number. So then finish write the reactant, then the product. So outside the parentheses, you will write the product nucleus. So in this case, will be nitrogen 15. The inside will be those small particles. So we have this helium-24, which means alpha particles. So you can write alpha particle. So therefore, the answer looks like C. All right. So the next question is, let's say, a particular smoke detector contain this much radio decay rate of American cesium 241. So with a half-life of 458 years, and the isotope is encased in a thin aluminum container, and I want to calculate the mass in gram of AM241 in gram in the detector. In the detector. So what do? You will use the Reed law, which is written as rate equals K times N. So K is the rate constant, and N is the number of those radioactive nucleus. So once we find out those N, we can convert from number to moles, then use mole mass to find out the grams. Okay, so to do that, we first need to do some conversions. One conversion is we convert 2.75 micro CI to the so-called disintegration per second. So shorthand notation is DPS. So that pretty much gives us how many those radioactive nucleus decayed. So that gives us some idea about how much those radioactive nucleus in the sample. So to do that, you are using this few equation here. So one equation we use is CI. What is CI? So the other equation you want to use is those prefix micro. So micro equals 10 to the negative 6. So therefore, we were starting with 2.75. So the Greek letter micro CI, and use our typical conversion fractions. So we can write so 1 micro CI equals 10 to the negative 6 CI, and this should come from this equation. So the next conversion fraction, it will come from this equation. So we will write 1 CI and 3.7 times 10 to the positive 10 DPS. So therefore, we just take these two fractions and we get 101750 DPS. So therefore, we find out this rate. Next, let's find out what is the K. If we find out what is the K, then in this equation, only N is unknown. So to find the K, we will use the half-life. Before use half-life, we have to make sure the units are okay. So this given half-life is in years. Here, DPS, so disintegration per second, per second. So therefore, one easy way to solve the problem is to convert that half-life from year to second. So we write 458 year and over 1. Then we know in 1 year, typically we have 365 days. And we know in 1 day, there will be 24 hours. And in 1 hour, there is 60 minutes. And then in 1 minute, there are 60 seconds. So therefore, we have 1.4443 times 10 to the positive 10 seconds. Okay, so let me reach that on the right 10. All right, so now we can use this half-life in second to find out the K. It will be per second. So therefore, K equals ln2. The number coming from logarithm function have no unit, and divided by t1/2, which is half-life. So divided by 1.443 times 10 to the positive 10 s. I just use s now, and you do the divide. So you get 4.7990 times 10 to the negative 11 to the 1/2. Okay, now basically we have everything we need to find out the number n in this equation. So we know what is K now. So this n will be our unknown question mark. So let's do that. We have 101750 DPS means this integration. I'll use abbreviation per second. So equals K times n. So K just find out 4.7990 10 to the negative 11, 1/2, then times n. So solve this equation for n, and we have Okay, so I shall write underneath this. So solve this one for n, we'll find out 1.101750 divided by 4.7990 times 10 to the negative 11. So that's it. This integration per second, and here just per second. So therefore, we find n, how many disintegration, how many disintegration, that means we have how many particles. All right, so therefore you find out n equals n equals 2.1202 times 10 to the positive 15. Okay, so finally we can use the Avogadro number and the model mass to find the mass. So we'll start with the number. We just find out how many radioactive nucleus in that smoke detector, and then we have this number. So we use our Avogadro number. So one more will be 6.022 times 10 to the 23, and then we will see one more for this given nucleus is 241 gram. So therefore we find out 8.49 times 10 to the negative 7 gram. So therefore the answer is E. Okay, so the next question is question 6. So a rock contains 0.357 milligram of lead-206 for every milligram of uranium-238. The half-life for the decay of uranium-238 to lead-206 is 4.5 10 to the negative 49 years. How old is the rock? So we want to use the equation like that. So because those information give you all in mass. So the equation you want to use is mass at time t. So for the radioactive dating, t is so no. So then when the rocket started, the t years before. Okay, so therefore this will be the mass 0 equals negative k times t. Okay, so we're assuming when the rock is formed T years ago, it has no lead-206 in it, and all the lead-206 come from the decay of uranium-238. In this sense, the amount of uranium-238 in the rock decreases as the year passes by. We can use the equations to find out how many uranium-238 decayed to produce this 0.357 milligram of lead-206. So the equation for the decay of uranium-238 to lead-206 is multiple steps. But if you adding up all those many steps, the net total equation will be this. So from this, we can see the coefficient ratio, and that is very important for our conversions. So just one uranium-238 produces one lead-206. All the other products is irrelevant. So once we find out the mole ratio between the uranium-238 and the lead-206, then we can start in the conversion or find out how much gram, how much milligram of uranium-238 is used to produce this much milligram of lead. So you can start with write 0.357 milligram of lead to 6, and so our typical conversion or the stoichiometry calculation is converting from like a gram to mole, then from mole to mole, then from mole to gram, then to milligram. So I think I will write those too long. Let's see. So you first want to use 1 gram is 1,000 milligram. Therefore, we have this amount of gram. Once you have gram, you can use one assumption. So if I have those notation like 2,6 and 238, even though they are not exactly the mole mass of those isotopes, but to a good approximation, you will call this the mole mass. And this also mole mass. So both of them mole mass. So this is the after we conversion. So this milligram comes out. We get a gram of lead. So lead 206 mole mass is 206. Therefore, you write 206 gram here, and then 1 mole here. Then we have that conversion ratio. See, we have 1 more lead and then 1 more uranium. So that's kind of out. And then we will use the other mole mass. So 1 more of uranium is 238 gram. So then finally you want to convert it back into milligram. So use 1 gram is 1,000 milligram. Yeah. So this is the conservatively all those conversion fractions you are going to use. So obviously you can see there's a lot of cancellation. So those gram come out, more come out, more come out, and then gram come out. So finally you just left over with how much milligram, and this 1,000 also comes out. So what's really important in the calculation is you can, so if I write this equals 0.357 and then times a fraction, so this fraction will be 206, then 238. So therefore, that become much simpler if you have a problem in the test. What you do, just take the given milligram lead, multiply by 238 divided by 206, get how many milligram of uranium used. So this is one way to speed up the process. So that's milligram of uranium-238. All right. So now we will say long time ago or 2 years ago, the rock has more uranium. How much more? So if we have like for every 1 milligram of uranium in the rock now, and 2 years ago, the rock will have 1 milligram plus 0.412 milligram of uranium, because this 1 milligram is still here and still here. But beside this 1 milligram, there is this much milligram that is reacted or converted into lead. Therefore, adding together is how much milligram that rock has. for every 1 milligram the drug has right now. Right. So basically, we find out this ratio here. Okay? So this ratio on the top will be 1. Then this mass 0 will be 1.412. So we're almost ready to find out T. So before we do that, we have to find out K. So we will use the equation as what we did in the last program. So K will equal Ln2 divided by T1/2. And you do that, you will see this K equals Ln2, the half-life for the uranium given in years. So that's okay. Then we'll find out our time T in years. So this 4.5 times 10 to the positive 9 years is the half-life of uranium-238. So we find out this K is 1.54 times 10 to the negative 10 and year to the negative 1 power. Right, now we will use the equation. So we will use Ln mass SAT. So now all divided by the mass of long time ago, T years ago. So therefore that become as what we represent. So right now for every 1 milligram of uranium, we have 1.00 plus 0.412 milligram T years ago. So to this conversion, so this will equals negative K times T. And then just use your calculator to find out this number. So this number will become negative. Let me change my pen. Okay, so get negative 0. Negative 0.3450 equals negative 1.54. Negative comes from the formula, okay? And then we have this K. Then times T. We're solving this equation for T, negative 0.3450 divided by negative 1.54 times 10 to the negative 10 year to the negative 1. That has no unit, equals T. We solve it for T, 2.24 times 10 to the positive 9 years. So the answer is D. Okay, so next question is very similar. So about radio decay. So this is the cesium-137 has a half-life 30.2 years. The component of radioactive waste from a nuclear power plant. If the activity due to cesium-138 in a example of radioactive waste has decreased to this much of initial value, how old is the sample? Okay, so by reading this sentence, radioactive waste has decreased to 45.2% of its initial value. So this sentence tells us that mass T, so what it has now, equals 45.2, and mass 0 equals 100. So therefore, we can use our one equation is Ln mass T divided by mass 0 equals negative K times T to find T. To do that, we will first find out what is K using this K equals Ln2 divided by T1/2. So we using the half-life 30.2, so we find out K equals 0.02295 per year. So now we are ready to take this mass T, mass 0, and get into this equation with K. So therefore we have Ln 45.2 divided by 100 equals negative coming from the formula, and then we find K is 0.02295 and year to negative 1, then times T. So solving for T again, and so we first get this Ln 45.2 divided by 100 is negative 0.7941. So take this number divided by a K, negative K, so negative 0.02295 year per year, and that equals to K equals to T. So therefore T equals 34.6 years. 34.6, therefore the answer is A. Okay, number 8 is about energy from nuclear reactions. So number 8 tells us electricity is generated in space vehicle from the heat produced by the radioactive decay of plutonium-238, and the given equation is this. So we have 238.94 plutonium produce 234.92 plus helium particles. Then give you the atomic mass of plutonium-238. So the reactant is 238.049554. Then the two product has the mass 2034 and then 4.0. So then ask us how much energy in kilojoule is released when 1.22 gram of plutonium-238 decays. So then I'll give you the conversion between gram and AMU. So to solve the problem, you will first to find out the mass loss. So that mass loss will call that delta M. So delta M will equal the mass of the product minus the mass of the reactant. So we have two products. So these two are the products. From the given problem, just be carefully enter those numbers in your calculator, and this is the reactant. So you do subtraction, you see the mass loss. So this mass loss is converted into energies. So what you do, you are first using that information we have here between gram and AMU to convert this much of AMU per plutonium atom, and that's also important because this calculation is based on this equation. From this equation, if those numbers give you as AMU, then you know it's for all those atoms. So you can see there's one atom of plutonium, then one atom of uranium, then one atom of helium nucleus. So therefore, we see this much mass loss is per plutonium atom. And what you do next, just take the number you get in AMU. So you have negative 0.007102 AMU, and we have this equation. So we have the Avogadro number of AMU, and so that amount of AMU will be 1 gram. So the AMU count out give you how many grams. So in the calculation, in the formula, like that formula we want to see is E equals delta MC squared. So you need this one in kg, kilogram. So what you do, just one more step. So 1,000 gram and 1 kilogram. The negative 1.179 times 10 to the negative 29. The units, very important, will be kg per plutonium atom. So it's still this much loss for one atom. Okay, so then here, see the equation, we want to find out the E. So therefore our delta M for this guy is negative 1.179 times 10 to the negative 29 kg per plutonium atom. Okay, and then I want to multiply by C squared. So you know what is C? Speed of light is a constant. So what I'm writing now is C as units meter per second, and you square this. All right. So if you multiply and what you get is this number. So negative 1.0614 times 10 to the negative 12. Let's see the initial units. You can see there's a kg, and there's a meter squared, and the second per second squared, and per plutonium atom. So that's actually turned out kg times meter squared divided by second squared is joules. So therefore, that'll become negative 1.10614 times 10 to the negative 12, and actually joules. Let me write them a little closer so we can write the units on the same line. Okay, so then you probably notice there's a negative sign. What this means, negative means the energy emitted. So that's all about this negative. 1.0614 times 10 to the negative 12. We know that will be J than 1 plutonium atom. All right, so now we want to find out how much energy in kilojoule can be produced by this much gram of plutonium-238. To do that, probably we will first find out how much atoms of plutonium in that 1.22 grams. So you can start with use molar mass and Avogadro number. So you write 1.22 gram of plutonium-238. So then we know how much more, 1 more is how much gram. So that's what we did before. We can use molar mass as a very good approximation. I mean the mass number as a molar mass, but technically the definition is not the same. Then we use Avogadro number. We use Avogadro number, which is this number. So gram comes out, mole comes out. So we have how much plutonium atom? 3.087 times 10 to the 21 plutonium atom. Okay, so that is how much joule per atom. Then we have this much atom. Just simply multiply them, but converting to kilojoules. So we have negative 1.0614 times 10 to the negative 12 joule per plutonium atom. And then let's see, we have this much of plutonium atom, 3.087 times 10 to the 21 plutonium atom. So the plutonium atom comes out, you get how much joules, but to convert into kilojoules, just do one more conversion. The joule comes out. So therefore, we find out this negative 3.28 times 10 to the 6 kilojoules. Then we have the word released means negative sign. Okay. So therefore, in the answer, you pretty well know see that choice have the negative sign because you see the word released. So therefore, our answer will be C. Circle that. Okay, so next question is about the test on human objects along the east coast of the United States in 1965 to 1966. Followed the era of atomic bomb tests, revealed quantity of about 2.5 pico-Ci of plutonium radioactivity, which is alpha radiation in a test subject. And that test subject, let's say a person has 75 kilogram is exposed to this radiation for 1.00 years, which means 365 days. If each alpha particle deposits 8.00 times 10 to the negative 13 joule, A, what is the number of rads absorbed by the person? What is the effective doses in REM if the RBE for the alpha radiation is 10? Okay, so this something kind of new is about this unit. So for part A, the question is asking for rad. So what is rad? Rad standing for radiation absorbed doses, which is 100 times the joules of radiation energy absorbed per kilogram of body weight. Assuming all the radiation energy from the alpha particle, each alpha particle gives 8.00 times 10 to negative 13 joules. Then in that 1 year period, test period, alpha radiation rate is this much. So which can be converted into disintegration per second. So then once we have the disintegration per second, and then we can find out how many particles that person received. So then if we know how many energy for one alpha particle, then we can find out how much radiation energy the person received. So then we'll divide by the 75 kilogram to get the so-called then times 100 to get the rads. So to do that, we'll first have to convert this 2.51 PCI into disintegration per second. So we will take 2.51 PCI. So again, those prefix. So 1 pico equals 10 to the negative 12 to the prefix. Therefore, we see 1 PCI that will equals 10 to the negative 12 CI. And then we have in one question, we know what is CI. So 1 CI is 3.7 times 10 to the positive 10 DPS. So that become 0.009 9287 DPS. Then next, DPS means this integration per second. So the time unit is second. So therefore, we want to convert a 1 year test period into how many seconds. So we start with 1.00 year. And then we see for every 1 year, 365 days, 1 day, 24 hours, and then 1 hour, 60 minutes, and 1 minute, 60 seconds. So finally we get 3.1536 10 to the 47 seconds. Okay, so then we'll use the decay rate and then this time to find out how much alpha particle decayed onto the object. So we have a 3.1536 times 10 to the 7 second or 1. Then the DPS means 1 second. How many disintegration? So we find out 0.07955 disintegration. So that gives us 2.9287 times 87 times 10 to the positive 6 disintegration. Oh, this is how much alpha particle deposited on that person. So then by definition, what is red? Red, so red equals 100 times how much joule per kilogram. So 100 comes from the conversion between units. From conversion or the definition of red, of Barcure to red. Right. So if you don't multiply by 100, you get the so-called Barcure, BQ. Right. So we find out how much alpha particle deposited. 2.9287 times 10 to the positive 6. That's it, this integration. And for every disintegration of alpha particle, for every disintegration of alpha particle, which is information given in the question, it will produce this much joules of energy. So then you have to divide by the kilogram. So this definition of Barcure or red. So the given information is 75 kilograms. So you get 3.12 10 to the negative 6 reds. Okay, so that's finished part A. We find out this much reds. Part B, we need to find out REM. REM is standing for Roentgen equivalent format. Roentgen is the scientist's name. we need to use red. So red is, we need to find out, then RBE. RBE standing for relative biological effectiveness. So even though you receive that much of energy, so the energy might come from alpha decay, beta decay, then those different decay modes have different damage power on the biological system. So for the alpha radiation, the RBE is the largest. So usually we're assuming it's 10. So once we know that, so then our question for the REMs, REMs will be simple. For equal to red times RBE. So the red we just find out 3.12 times 10 to the negative 6. And then you just times RBE, RBE is 10. So therefore get 3.12 times 10 to the negative 5. So therefore you compare all those, the answer is negative 6, negative 5, 3.12, so it's D. Okay, so the answer is D. All right, so the last question is which particle has the highest penetration power but has no mass number? So have no mass number. Alpha particle has a mass number. Beta, positron, electron, gamma ray. They all don't have mass number. Even though electron, positron, or beta is high speed electron, they all have mass. So this for they have no mass number. And this has mass. That has mass, but don't have mass number. Why? Because mass number, by definition, is the number of proton plus number of neutron. So in electron, we don't have proton. In a beta particle, we don't have. We don't have proton. We don't have neutron. So therefore, so you possibly can say the answer is the beta, positron, electron. The highest penetrating power with the gamma ray. Right. So therefore, you can remember those sequence. So in the increasing order of penetration power, alpha will have the lowest penetration than beta than gamma. So even though alpha penetration lower, but the damaging power is higher. So that's once if the alpha particle get inside the biological system organs, then the damage can be 10 times stronger. But sometimes even the air or skin or very thin slice of paper can stop the alpha particles. All right. So therefore, the answer is E. All right. So that's all for chapter 21 practice.